Hello ladies and gentlemen, this is George Kamiti. Welcome back to our channel. We are analyzing thermostresses and strains. And our today's problem is saying this. A composite bar made up of aluminum and steel is held in between two supports as shown in the figure below. The bars are stress-free at a temperature of 40 degrees Celsius. What will be the stresses in the two bars when the temperature is 20 degrees Celsius? If 1. The supports are non-yielding and 2. The supports come nearer to each other by 0.1 millimeters. Young's modulus of elasticity of steel, 210 giganewtons per square meter. That one of aluminium, 74 giganewtons per square meter. The coefficient of linear expansion of steel is 11.7 times 10 raised to the power of negative 6 per degree Celsius, whereas that one of aluminium is 23.4 times 10 raised to the power of negative 6 per degree Celsius. This is aluminium bar, this is steel bar. The circular or these two circles are used to show that the cross sections of the two bars are circles. Diameter of aluminium bar 25 millimeters, that one of steel bar 50 millimeters. Length of aluminium bar 0.3 meters, that one of steel bar 0.6 meters. The supports holding the aluminium and the steel firmly together are supports L as well as M. We are going to assume that the support L is removed so that the bar contracts freely. The contraction of the steel bar, that is the free expansion of the free bar, will be given by coefficient of linear expansion of steel bar multiplied by the change in temperature multiplied by the length of the steel bar. This is going to give us change in length in steel bar being equal to the coefficient of linear expansion of the steel bar, which is 11.7 times 10 raised to the power of negative 6. Change in temperature. Initially the temperature of was 40 degrees Celsius. It has been lowered all the way to 20 degrees Celsius. Therefore, the change in temperature is 40 minus 20, which is 20 degrees Celsius. The length of the steel bar is 0.6 meters. So we multiply that by 0.6. And the extension or the contraction of the steel bar is going to be 1.404 times 10 raised to the power of negative 4 meters. On the other hand, the contraction of the aluminium bar will be given by the coefficient of linear expansion of aluminium times the change in temperature times the length of the aluminium bar. This is going to be, the coefficient is 23.4. So we got 23.4 times 10 raised to the power of negative 6. Change in temperature 20 degrees. The length of aluminium bar is 0.3 meters. This is going to give us a change in length in aluminium, changing length of 1.404 times 10 raised to the power of negative 4 meters. Therefore, the total contraction of the bar, total contraction of the composite bar or the composite material will be given by the contraction of the steel bar plus the contraction of the aluminium bar. So this is going to be 1.404 times 10 raised to the power of negative 4 plus 1.404 times 10 raised to the power of negative 4. And this is going to give us a total contraction of 2.808 times 10 raised to the power of negative 4 meters. if a load P is applied on the support L as well as M, yeah, we are going to have, let a load P be applied on the supports. Be applied on the supports, that is support L as well as support M. So this load applied on support L, that is on aluminium, is equal to the load applied on the steel. We know this from stress is equals to load over area. It means that load is given by stress times cross-sectional area. Therefore, the load on the, that is the load applied on the aluminium bar, will be given by stress developed in the aluminium bar times the cross-sectional area of the aluminium, which will be equal to the load applied on the steel bar will be stress in the steel bar times cross-sectional area of the steel bar. When we make a stress in the aluminium, the subject, we are going to have stress in aluminium is equals stress in steel times area of steel divided by the area of aluminium. The area of aluminium. And this is going to be stress in steel times cross-sectional area of steel is going to be pi over 4d squared, whereas that of aluminium will also be pi over 4d squared. Steel have got the largest diameter, so we are using capital D, aluminium small d. Pi over 4 will cancel out with pi over 4. So we are going to have stress in aluminium is equals stress in steel times diameter of steel, which is 50 millimeters, therefore 50 squared divided by the diameter of aluminium, which is 25. So that is d squared, 25 squared. And this is going to give us stress in aluminium being equal to be 4 times the stress in steel. The stress in steel. Good. So this relation, we are going to use it in a few. From there, we are going to determine the extension of the steel bar due to the load P. Due to this load P that has been applied on both supports. And in this case, we know this. The Young's modulus of elasticity is given by stress divided by strain. So when you make strain the subject, strain will be equal to stress divided by the Young's modulus of elasticity. Therefore, the strain in steel will be given by stress developed in steel divided by the Young's modulus of elasticity of the steel. And we know that strain is given by changing length divided by the original length. Therefore, it means that the strain in steel will be changing length in steel divided by the length of the steel, which will be equal to the stress in steel divided by the Young's modulus of elasticity of steel. When we make extension in steel the subject, we are going to have the extension in steel will be equal to stress in steel over Young's modulus of elasticity of steel times the length of the steel bar. And in this case, we are going to have this. The extension of the steel bar will be equal to the stress in steel bar divided by Young's modulus of elasticity of steel is 210 giganewtons per square meter. We convert to newtons per square meter, multiply that by 10 raised to the power of 9. Then we multiply this by the length of the steel bar, 0.6 meters. And this will be equal to 0.6 stress in steel divided by 210 times 10 raised to the power of 9. So that is the extension of the steel bar. Then the extension of the aluminium bar, extension of the aluminium bar due to the load P, due to the application of the load P on the support L. So the extension will be given by, using this relation, the extension in the aluminium bar will be given by stress developed in aluminium divided by the Young's modulus of elasticity of aluminium times the length of the aluminium bar. So this will be equal to the stress in aluminium, we had it as 4 times the stress in steel. So we are going to substitute that one here. So 4 times the stress in steel over the Young's modulus of elasticity of aluminium, which is 74 giganewtons per square meter. We convert to newtons per square meter. Then we multiply by the length of aluminium, 0.3 meters. 0.3 meters. That is going to give us the extension in aluminium, an extension of 1.2 stress in steel divided by 74 times 10 raised to the power of 9 newtons per square meter. And from there, the total extension of the whole combined component, the total extension will be given by the extension of the steel plus the extension of the aluminium bar. Extension of the steel is, we got it here, that is 0.6 times stress in steel divided by Young's modulus of elasticity of steel, 210 times 10 raised to the power of 9. We add that to the extension of the aluminium bar, 1.2 stress in steel divided by 74 times 10 raised to the power of 9 is equal to the total extension. We had it as what? 2.808 times 10 raised to the power of -4. So that is the total extension of the whole component. Good. What we are going to do, we are going to remove this 10 raised to the power of 9 by multiplying each section by 10 raised to the power of 9. Then we divide 0.6 by 210. So 0.6 divided by 210, that happens to be 0.002857 stress in steel plus 1.2 divided by 74, that happens to be 0.0162 stress in steel is equals to, this one is 2.808 times 10 raised to the power of -4 times 10 raised to the power of 9. Remember, you have removed this 10 raised to the power of 9 by multiplying everything by it. So here it's going to cancel out. It's going to cancel out at this point, but at this point we are going to have it there. So when we add this to 0.002857 plus 0.0162, we are going to get 0.019057 stress in steel being equal to 2.808 times 10 raised to power -4 times 10 raised to power 9. That happens to be 280,800. 280,800. To get the stress in steel, divide both sides by this. So we are going to have stress in steel is equals to 280,800 divided by 0.019057. That happens to be 14.73 times 10 raised to the power of 6 newtons per square meter. Newtons per square meter, which can also be rewritten as 14.73 meganewtons per square meter. So that is the stress developed in steel when the supports are non-yielding, that is, they don't experience any form of movement whatsoever. Then the stress in aluminium, we have it here as 4 times stress in steel. So that is going to be 4 times 14.73 meganewtons per square meter. So when we do that, we are going to get a stress of 58.92 meganewtons per square meter. So that is the stress in aluminium bar when the supports are non-yielding. So we have answered part 1 of the question. That is part 1 of this question. Part 2 of the question is asking us to determine the stresses in the bars, in the two bars, when the supports come nearer each other by 0.1 millimeters. So we are going to have a different total extension. The total extension will now be given by 2.808 times 10 raised to the power of negative 4 minus, they come to closer to each other by 0.1 millimeters. So when you convert to meters, that is going to be 1 times 10 raised to the power of negative 4. And that is going to give us an extension of 1.808 times 10 raised to the power of negative 4 meters. So that will be the total extension. Therefore, the stresses in both steel and aluminium, let's use this part here because we are not going to have any major changes. The only thing that will change is the total extension. That is the only thing that will change. But these other values will remain the same. So we are going to have this one, when we add these two, we get 0.019057 stress in steel being equal to 1.808 times 10 raised to the power of negative 4 times 10 raised to the power of 9. Remember, we removed this 10 raised to the power of 9 by multiplying each part of this equation by 10 raised to the power of 9. So this is going to be 0.019057 stress in steel, which is equal to, when you multiply this these values, we are going to have 180,800. So when you divide both sides by 0.019057, divide this side as well by 0.019057, we are going to have a stress in steel, a stress of 9.49 times 10 raised to the power of 6 newtons per square meter, which can be rewritten as 9.49 meganewtons per square meter. So that is the stress in steel when the two supports come near each other by 0.1 millimeters. On the other hand, the stress in aluminium is 4 times the stress in steel. So that is going to be 4 times the stress in steel, 9.49 meganewtons per square meter, which is going to be 37.96 meganewtons per square meter. So we are through with this problem, and that is the solution for this question. Thank you very much for watching our video. Please do subscribe if you are not yet a subscriber, and thank you very much for your continued tireless support. Thank you. Let's meet in yet another lesson.